All right, welcome everybody to the second lecture in the Introduction to Deep Learning course at TUM. So in the last lecture, we've talked a little bit about, what you can do with deep learning, talked a little bit about the history in deep learning. We've also introduced a few things that our research labs here at TUM are working on in that specific field. Now, today I would like to go a little bit more technical and start with machine learning basics, which is a prerequisite for deep learning. I don't want to, go into all the machine learning methods, but I would like to introduce the concepts that we will later need for the specific development of neural networks. So when we're talking about machine learning, we typically start by talking about a task. And there's a wide range of tasks that we could imagine. In the previous lecture, we already saw that a lot of the motivations behind deep learning are from computer vision. In computer vision, we want to, on a high level, make a machine understand the real world. In a sense like how we humans understand real worlds, we can perceive real worlds. And this kind of perception system we want to remodel with a machine learning method. Now, even in computer vision, there's a large variety of different tasks. And I don't want to go into all of them in detail right now, but rather I would like to start very, very simple first. And one of the canonical tasks that typically people, start looking at first is looking at a set of images. And these images, we have typically, in this case, we have one object in there. In this specific case here, if you're looking closely, we have two types of semantic objects in there. And one of them is dogs and one of them is cats, right? So we see, in this case, we are very interested in figuring out, is it an image with a dog or is it an image with a cat? And this is a very simple task, which typically we refer to as image classification. Image classification in this case means that we would love to assign or predict a label to the respective image that the machine sees or the method sees. And then in this case, assign it either, is it a cat or is it a dog? In this case, we have these two labels. You see this with the boxes. So either we have orangey boxes that correspond to the cats, or we gonna have the bluish boxes which correspond to the dogs. And the task now of our method is give me an image that you want to analyze, understand, and the method should propose one of these two labels. In this specific case, we typically refer to it as binary classification. It's a special case because we only have two different labels. In this case, we have cat or we have dogs. Now, this is of course a already very challenging task. And if you're just going on Google image search, for instance, and we're typing in cat, we're already seeing that we're getting quite a couple of different images here for cats, right? This is like what in this case on the Google data search, Google image search, what they will return to you. In this case, we already see there's a couple of differences that make this task actually pretty difficult, right? There's different poses, how does the cat pose? What kind of 3D position does the cat have with respect to the camera? What illumination we're considering? Is it bright? Is it a white background? What kind of appearance does the cat have? What kind of fur type? What color? And so on. So you already see this task is pretty difficult. There's even harder cases why this task is difficult. We see occlusions, right? So in this specific case, right, we see here there's a white bar in this image here. There's just a lot of stuff occluded. In the image itself, we're gonna have the cat is actually wrapped, and we only see one part of the head. And we as humans, we're actually still pretty good at seeing, oh, this is a cat, right? Or well, we're pretty sure about it. Of course, if too many of the things are being occluded, we're also struggling. We might have other problems in the images like background clutter, right? We see here basically a white foreground and a white background, and I'm assuming this is a husky dog who is on a white background, and since the fur is already white, it's very difficult actually to spot the differences here. Here, this cat is on a dark background, it is very difficult again because the background and the foreground are very similar. But there's not just color differences in terms of foreground, background, and occlusions. There's also semantic differences, right? For instance, here we are seeing a cat that is actually a cartoon drawing. And the problem in this case is if we are seeing cats like that, well, we humans understand it, and we understand it surprisingly easily. Even we haven't seen that many cartoonish cats. I'm sure we have seen a few of them, but compared to real cats, we've only seen a very small size. And these kind of representation differences is actually something that is very, very difficult, as we will see, for machine learning methods. Now, especially representation, that's why I'm mentioning it here, is one of the big changes. So if we're taking all of this together, we already can very quickly see, by just saying, oh, look at my image color or something like that, it is very difficult actually to perform this task of image classification, right? And yeah, the question is actually, how do we do that, right? Intuitively, we as humans, we kind of have this understanding, but it's very difficult to describe, like, how do we humans understand it? And because of that, it is a very difficult task how we can actually teach a machine to do it. Now, if we're talking about machine learning, what we want to do is we would like to, we would like to perform this task, right? We want to have a method and a learned model, in a sense, that helps us to perform this task. Now, the idea of machine learning is we don't just go ahead and describe the algorithm completely, like how, like, oh, look at the eyes and then look at the legs and so on, because this is actually pretty difficult if we had to do this by hand. We will see people have tried similar attempts to kind of describe these features by hand. But in fact, machine learning is, we want to do this from data. This is kind of the experience that we accumulate. And with this data, we would like to train a model and make the model learn what we have kind of told the model from the data, right? What the model can extract from the data. Yeah, and with this kind of experience, it's kind of in a similar sense what little babies do when they see, oh, we're seeing the world, right? We're getting some hints. Like parents, for instance, tell us, oh, this is happening, that is happening, this is that object, this is that object, and so on. And in the same way, we're trying to do it actually with the machine learning model, where now we have a bunch of data and we may have some annotations in the data. We may have some meta information that we can use for the learning, like labels. Is it a dog? Is it a cat? And so on. This actually brings us to very important types of categories in machine learning. So typically we are distinguishing two types. In practice, we are distinguishing unsupervised learning methods and supervised learning methods. And the distinction is relatively, self-explanatory. In the unsupervised learning case, we don't have any labels, right? This is what I mentioned. Like, we don't have meta information that tell us, oh, this is a dog or this is a cat. And in this case, we don't have a specific sense even what labels are, because we never annotated them. In fact, we simply, in an unsupervised learning case, we simply want to find out the properties of the structure simply by looking at the data, right? In simple unsupervised learning methods, you might even know, right? You might know how a PCA, principal component analysis, or k-means clustering. In these kind of methods, they are unsupervised, because what they're doing, they're just trying to find clusters essentially in data, and based on these clusters, they're going to divide the data into these clusters. And but very careful, there's no semantic meaning attached to the clusters by definition yet, right? As soon as we want to have, like, saying, oh, this is a specific class, this is a specific type, then we're already going into the supervised realm. Well, to give you a few examples, right? For instance, if we're running a clustering on images, we may end up that we're dividing the cats and the dogs here. But this is pure random coincidence here, right? Like, if we're saying, oh, like we do it based on the greenish color of the background, then we would basically cluster this image and that image together. So this is like, it's totally dependent on what clustering method you use, and the method itself already decides how the clusters will look like. This is how we interpret the data. Nonetheless, at the end of the day, what we would love to do, we would like to find some sort of decision boundary in the clusters. This is this line here. This decision boundary, we will later get into it a little bit in more detail. This is what tells us, after we've learned this boundary here, or this decision boundary here, we can then go test time and apply the same boundary and divide the two classes respectively, right? In the end of the day, what people often do, they use simplified abstractions for the samples. In this case, we could say we have these crosses and these circles. This is, often what's being done in literature. So it's getting a little bit more clear, what we want to abstract here. Okay, so this is unsupervised learning. The other side is the supervised learning. In this case, we do in fact have labels or target classes. So let's say we have a bunch of images, right? What we do have in this case, we don't just have this like random collection of images, but in fact, we also have the respective semantic labels to it. And these labels are typically done by somebody who created the data set, right? Some annotator who went ahead and literally said, well, this image is a dog, this image is a dog, this image is a dog, this is the cat now, another cat image, and so on. And in fact, in research, a lot of people have been doing this for quite a while, right? They went through data sets of images and they have provided these labels. And in this case, these supervised labels, so these labels are typically the basis for supervised learning. Now, if we are going back to our task, the question is, how do we actually learn image classification? Oh, yeah, one thing I can already say, like in this lecture, we will most likely deal with supervised cases. This is mostly the standard assumption we're gonna make. If we're talking about performing image classification, this is what we would like to do. What I said is we have this data. But the question is, how do we actually know that we're learning something, right? And there's a very important distinction in learning between memorizing things and learning, meaning you channelize from learned things to new things you haven't seen before, right? So in other words, what you really care about is, I have seen hundreds of thousands of dog images, and if I see another 100,000 of dog images, the question is, how good is my method at these newly seen dog images, right? So you basically, like we humans are pretty good at it. We're very good at abstracting to new situations, and we don't have to have this very same image what we have seen before. We don't just memorize, but we do channelize. In machine learning, in order to do that, we typically divide our data into training data and into the test data. And this is pretty much doing what I just said, right? You take the training data, you use that data in order to train your model. And then once you have trained your model, you look at the test data and see how well your model is doing. And this is giving you some measure of learning. Learning means not just looking at the training data, but in fact looking at how well do we do then on the test data. This generalization setting is what we really care about, right? If you just memorized a bunch of samples, that's not so interesting, right? That's more like a dictionary. But in fact, we really care about to generalize. And we will go into detail about this one. But practically what it means, we're not looking for like exact matches in the training set, but we're trying to accumulate commonalities in the training data that we can later on apply in new situations. Simple example, if you're looking at cats, right? They do have 4 legs. They have kind of fur, they have a head, they have face, they have eyes, and so on. And these kind of informations, we accumulate sort of in our model. We're learning these features, we're learning this kind of stuff, and then later on we can apply it to the test data. Now, the underlying assumption here is that the training and the test data is actually from a similar distribution, right? And this is a very, common problem in a lot of research works is that there's a data set that gives you a training and test set, right? It's divided into 3 parts. We'll get into this in a second. There's a validation set too, but we're going to have a training and a test set. And one of the problems is often that, these things don't reflect the real world. And a specific scenario is if you're looking at self-driving cars, there's a lot of data set for self-driving cars, but these data sets do not necessarily cover all situations that real world situations have, right? Like for instance, you will barely find any data sets that cover like tricky situations where there was an accident and what should you do there, right? And this is a very important understanding of machine learning is, we have this assumption that the training data has a similar distribution. We're always talking about distributions here because we're assuming we have a large enough corpus of data and we kind of hypothetically have this virtual distribution of the data, and we're hoping that the test and the training data comes from the same distribution. And because of that, we have the ability to transfer the knowledge, that we learned in the model at training time into the test time. Now, if you're going back, how can we learn the image classification task? Now what we're doing is we're taking the experience, the data, right? And we're using that in order to train our model. We'll see this in a few minutes, how that works. But now what we're doing is we're doing another step, and this is very common in machine learning, that we actually measure the performance, right? So we figure out how good is our image classifier right now. There's a lot of different metrics for for performance measurement. A very common one is accuracy. However, I want to make it clear that this is very specific to an image classification task that you would consider accuracy. Accuracy is very simple, right? You just see, oh, you have n samples. How many of them did you predict correctly? And you just get an accuracy out of that, right? That's a very simple measure. We're gonna deal a lot with accuracy at the beginning because we're gonna focus on image classification tasks. But there's other metrics like intersection of union, IOU, mean average precision. You will hear these kind of things a couple of times later in the lecture, but at the beginning we probably deal with accuracy for a while. So yeah, if you're looking at these kind of two realms, we have this unsupervised learning and supervised learning. You can already guess, well, we're looking mostly at supervised learning. For completeness, I would also like to mention reinforcement learning. Reinforcement learning is this kind of idea that is closer to unsupervised learning, where in this case we have kind of this global, we have this agent, right? We have an environment, we interact with the environment, and at the end of the day we're gonna get some sort of reward. In this case, yeah, we do give the environment, but there's like no supervision of where, you know, the agent should go and stuff. So this would be considered more on the unsupervised side. Again, for completeness, I would also like to mention that in the literature, you will often see things like self-supervised learning. And self-supervised learning is also somewhat in between unsupervised and supervised learning. But the idea is that you can get the labels for free, or you don't have to have human labor in order to annotate the labels. A very specific sample is future frame prediction in a video. Let's say I have 10 frames in a video sequence and I would like to predict the 11th frame, right? This is a self-supervised task because I can just simply take videos that have more than 10 frames. I get the ground truth information for free because I just look at the 11th frame in the videos and then I train my method to predict the 11th frame. Now, often what people try to do, they try to formulate tasks as self-supervised, you know, because they don't want to spend the effort of annotating the data. But I would like to clarify that this would still be a supervised task, right? You still have an annotation at the end. The only difference is the annotation is free, but it would still be a supervised training task. Yeah, in this lecture, don't worry about the other two things right now. We will later on talk a little bit about it, but for the first 3/4, I would say, or 2/3 of this lecture, we will look at the supervised case for the time being. Yeah, so this is like the main idea behind the machine learning, right? What problem settings we have. We have this data, right? We have some experience and we want to learn from this experience in order to make predictions to situations, in this case images that we haven't seen before. Now let's have a look how we do this technically. In this case, I would like to continue with this example that we had before. We would like to do image classification. And we would like to propose a very, very simple classifier. We don't want to use a neural network yet, we want to use something much simpler. And one of the most simplest classifiers that we can think of is a nearest neighbor classifier. So the idea of a nearest neighbor classifier is we do have a set of images in a data set, right? Like in this case, we have, again, dogs and cats. We do have the labels for it, meaning it's either a dog or a cat. And then we have a query image. And for this query image, we would like to figure out which of the other images in the data set is the closest one, is the nearest neighbor, right? So what we do is we have to compute a distance metric between that image we just queried. So, right, so in this case, we have this dog here, right? This is our query image. And now we just sort all the images in our data set by distance with respect to that query image, right? And then what we do is we just take the image that is the closest, meaning it has the smallest distance. In this case, it's this little dog here, right? So like, just assuming this is what our distance metric gave us. And now we just look up the label here. This is a blue frame. Blue frame corresponds to dog. And in this case, we would say, well, this classifier tells us the nearest neighbor was a dog. And because of that, we would assign and predict the dog label to this image here. Okay. There's a few variations of these nearest neighbor classifiers that are, kind of relevant. What we could do is we could say, let's not just take the nearest one, but let's take several of the nearest ones. So let's say we're taking the 3 nearest ones. In this case, these were the images that our distance metric told us were the closest to this image here that we queried. And And then we're just taking the majority vote here between these images and assigning the label according to the majority vote. So in this case, we have 2 cat images, right? 1 dog image. So 2 cats are the majority. We would assign a cat label to that dog. And this is called a k-nearest neighbor. Like in this case, we would assign a cat falsely, of course. I mean, assuming this one is actually a dog, which I would say it is. Then we would take these n nearest neighbors. K nearest neighbors. In this case, k is equal to 3, right? Because we took the 3 nearest neighbors. And the simplest one we had before was like the 1 nearest neighbor, the k equal to 1. So if we're actually visualizing that data, we have kind of this one parameter we can play around with, right? So we can say this k is telling us how many nearest neighbors we would like to consider. So let's say we have some data distribution here, right? These are samples. In this case, we have a couple of classes, right? We have green, red, and blue, right? For each of these labels here, for each of these data samples, we know which label it is. And what we would like to do now is we would like to associate like regions in this 2D plane to the nearest neighbors. So in other words, if we're saying we have a nearest neighbor classifier, we just say, well, if I'm trying to query this point here, I'm just figuring out which of the other points is the closest. So it's maybe this one here, right? So everything in this red region would be assigned as a nearest neighbor to one of these red points, right? And you see it, right? Like this line here goes right between 2 points, and so on. And in this case, we can essentially have these decision boundaries. I mentioned that before. So the borders here, they are decision boundaries. And they're telling us whether we should assign it to one or the respective other side of this boundary. So one label or the other label. In this case, you already see that the nearest neighbor classifier is actually pretty noisy, right? Because it totally depends on the samples here in our training data. And in this case, we would want to we want to make predictions for everything we're feeding in our input domain. And we already see there's a bunch of outliers here, right? So here we see, for instance, here we see one red outlier, which leads to this outlier region here, right? And maybe that's not right. Maybe we have like one outlier that is like, it looks like a specific class, but it's actually a different one. So we would like to kind of smooth this a little bit, regularize it a little bit. And this is then what the k-nearest neighbor classifier is doing. If you're taking k equal to 5, we would get something like this one here, right? And yeah, what do we get in this case? We see we get a bit more connected regions together here, right? And we also have the green ones and we have the red ones. So it's not so noisy anymore than here. So if we have a single outlier, it would not be such a big problem. There's an extreme case of that actually. When we're setting this k equal to the number of training samples, we will only get a single region, which is simply the majority vote of all the training samples for a class, right? So we see it does this voting, so it's less noisy in a sense. There's also another interesting question. In this case, we set k equal to 5, right? So we're taking out of the 5 nearest neighbors, we're taking the majority vote. We're ending with a bunch of regions where we have like white parts here. There's a simple reason, right? Basically, you might end up with 2 to 1, so there's no clear majority. That just might happen. But you can get around with it and then adapt the distances. You could change this a little bit. But let's have a look at the reason why I wanted to introduce this classifier is not for the sake of we actually want to do like nearest neighbor lookups, but I would like to make you a little bit understand how we would expect these classifiers to behave. And this is a very important concept later on when we're training the neural networks. Specifically, if we're training such a classifier, how do we expect that the nearest neighbor classifier would perform on the training set, right? So if I have 10 images, I have labels for these 10 images, I take one of these 10 images, I'm going to do a query, I would expect that I get the very same image as a nearest neighbor, right? Because my distance metric would be 0, it's an identical image. So in this case, well, if you're thinking about how would the nearest neighbor classifier perform on the training data, we would expect to always find this right nearest neighbor. In this case, we would expect to get actually a pretty good result, right? Actually, we would expect to get perfect results, right? Because we always find the right answer. If we're doing a k-NaN classifier, where k is equal to 5, for instance, it's going to get a bit trickier, right? We would, at the training data, we would take the 5 nearest neighbors. Well, we expect the best one to be among these 5, so one of them is right, but the other 4 might be all wrong. So we might still get a few wrong ones if we're setting k to something higher. However, the important thing about machine learning is not how we perform on the training data. Later on, this will be called overfitting. But in fact, we want to do more than simply memorize the training set. We want to, extrapolate, generalize. So the question is, what classifier is more likely to perform best on the test data, on the data that is not actually annotated, right? So we're taking a sample of the test set, we're trying to find nearest neighbor in the training set, and we're trying to figure out the labels in these nearest neighbors, right? So now the question is, what classifier is more likely to perform best on the test data? Well, if you're thinking about that one, and if you're taking a nearest neighbor classifier where k is equal to 1, we're just taking simply the best nearest neighbor. If this distance metric was a little bit wrong, we would maybe get only a single answer here, right? We would get maybe a wrong one, maybe a right one, but the variance is extremely high. So if we're setting k to something higher, we would get at least these close decision boundaries here, and we would expect actually to get better results on the test set. And in a sense, what k is doing here for us, it's helping us to regularize the problem, right? It's saying, oh yeah, let's make the training a little bit harder. We're not just memorizing a single sample, but instead of, we're trying to get some sort of majority vote and kind of aggregating information from multiple train images for a given query, right? So we would expect the test time, the k-NaN classifier would actually work significantly better. And I already mentioned, now the question is, how do we set this k, right? We don't know that necessarily. In this case, k is a hyperparameter. And in this lecture, we will be talking about hyperparameters for quite a bit, actually. This will be a thing later on, like what architecture we're using, what learning method, what optimizer. These are all going to be hyperparameters. In this case, in this nearest neighbor case, we're actually going to have a lot of different hyperparameters already. This is even a simple problem, right? So in this case, we already have an L1 distance as a potential distance metric. We have possibly an L2 distance. So the distance metric that we're using is a hyperparameter. Now, again, to clarify, this is a very simple distance metric. I'm not arguing this is a good metric to just, take the L1 norm in pixel space and compare two images. We will later see this is actually a very, very naive way to do it. But I just wanted to highlight this distance metric is already a very complicated hyperparameter we have to figure out. The number of neighbors, we already discussed that one, right? The k is a hyperparameter. And the challenge now basically is that these hyperparameters, they're actually going to be problem dependent, right? So depending on image classification, segmentation, or whatsoever, whatever we're going to do later on, these hyperparameters, they are problem dependent, right? And the big question is, how do we actually find these hyperparameters? And I've told you so far we have the training data and we have the test data to evaluate it. So how do we find the hyperparameters? And that's not so quite clear. So we have to introduce another type of data, and this is the validation data, in order to find the hyperparameters. Now, in practice, this is now the basic recipe that we're going to apply in machine learning is we're going to say, this is our entire training corpus. We do have training data on one side, we have validation data, and we have test data. And what we do is we split up all of our collected data into these three subsets, in the train set, validation set, and test set. Now, in order to find the hyperparameters, we can consider training and validation data. This data is kind of fair game. We can do whatever we want with it. Typically, what you would do is you would use the training data to train your model. And then you take your validation data in order to figure out how is this model working right now. If it's not working so well, like maybe it didn't optimize so well, we have to optimize more. We have to check how good our loss curve is. I'll later see that. Then we have to adopt some parts in our model and change some of these hyperparameters. And this is typically the validation set tells us if validation is bad, we have to change some stuff here and there. So all of these things we're going to use to find hyperparameters. A typical setting here is that we split the data into 60%, 20%, and 20%. Other splits are 80, 10, 10, right? There's a couple of different splits we could use. Depends a little bit how big your data set is, how accurate you want to have validation and testing, and so on. Here's a very important thing that I would like everybody to remember. Whenever you develop a method and you don't quite know whether the method works, whether the architecture doesn't work, always check the validation set. The test set is not for development. You're not going to go and say, hey, oh, how well is my method working? I'm going to look at the test set and so on. The test set is only supposed to be used once at the very, very end when you're done developing, when you're done training your model, when you're done hyperparameter optimization, then you're using the test data. Only once. The reason is very simple. If I'm going to run my test data and I'm going to use the information that I'm getting out of this run, let's say it worked very well for most of my classes. It was very good at classifying the dogs, but not so good at classifying the cats. In this case, I have to change my model. If I'm going to use the test information for that, I'm in a way cheating. I'm literally taking information that I'm going to use later on for evaluation in order to make design choices. So that would be considered cheating because you are using information of your evaluation in your training processes, in your hyperparameter optimization. And this is a very tricky thing. In a lot of research works, basically when people have data sets, they typically put a training, a validation, and test set online. And sadly, often people, they try it many, many times. They see how good they are in the test set. And if they're not so good, they're trying again, until they're great. But maybe the method didn't actually work so well. They just figured out how to bootstrap the test set. And in order to avoid that, a lot of benchmarks actually in research, they have basically submission websites where you download the test data without the labels, so you don't know the ground truth. You run your method, you're going to get labels for that, and then you upload the results to your test site. Many benchmarks are doing that. And in this case, you can only submit once in a certain time frame, like once every month, right? So in this case, it's very difficult to bootstrap your test data because you can only do it once. Of course, people try to cheat the system too, but that's not something you're supposed to do, right? The test set is supposed to tell you at the very end how well the method works, but not how well you overfit it to a specific, or how much you bootstrap the data. So in fact, the only thing to figure out how well your method works during development is during validation time. So that you take the validation set, you test on the validation, means you validate, you see how well it works. If it doesn't work so well, you adapt your method, you validate again, and so on. Okay, there's another thing that might be interested in this regard. There's a thing called cross-validation. I mentioned already the whole training data is kind of fair game. You can, the train and val, you can kind of arbitrarily mix and so on, depending on how you want to develop it. Many times people split the training data into n folds. So for instance, in the first run, you say, oh, this first chunk here, this first 20% of your training set is validation now, and these 80% here are going to be used for training the model. In the next run, you saying, oh, this one is now training, and then you go, this one's validation, and so on, right? So you kind of mix and iterate between your training and the validation part. This is often being used when you don't have a large training set, so you want to get more validation from different parts of your training to make sure these distributions match, and based on that you can make hyperparameter decisions. Okay, getting back, what we want to do, right? We have we have the training and the validation set, we have a test set, we're finding the hyperparameters and so on. If you're talking about cross-validation, question is, why do we do cross-validation and not just train and then test at the very end? Again, to reiterate, the test set is not supposed to give you information during development, during training your method. The test set is only supposed to be once at the very end, right? And please keep this in mind. I would like everybody who comes out of this class to understand that a test set is not for developing and bootstrapping your method. Okay, But this is the basic recipe for machine learning, right? We have some training data, we validate, and at the very end, we're going to test. There's one concept that I already highlighted a little bit now. We have these things called decisions boundaries. And this is the thing I would like to talk next about a little bit more in detail. So instead of using like a linear classifier to do nearest neighbor, I would like to tell you how we are finding this line here, meaning how we're finding this decision boundary. And we can then associate at test time or validation time, we can associate everything that is right to this boundary one label and everything that is left another label. In this case, I would like to talk a little bit about linear decision boundaries, meaning this is actually a single line here. We're in 2 dimensions, this is a line. We will later see when we go to higher dimensions, this will become a hyperplane, meaning that we will have an n-dimensional space of input features. We will have a hyperplane that separates that space, right? We can also have more classes and so on. In this case, I would like to talk a little bit about linear decision boundaries. What are the pros and cons for using linear decision boundaries? Well, if we're using, well, the first thing is it's very easy, right? That's the big pro. Because it's relatively easy to find these hyperparameters for this hyperplane. We can also say there's a lot of disadvantages, meaning that the distribution here must be clearly separated. We already saw in the first lecture when we were talking about the XOR problem, right, of this single layer perceptron. Yeah, if it's just linear, you can't explain all cases, right? We've seen that already. Okay, but I would like to talk a little bit about linear decision boundaries. Specifically, I would like to talk a little bit about linear regression, and I would like to take the opportunity to introduce some of our formulations that we're going to use across the course. I did mention everything we're going to look at right now is supervised learning, meaning that we do have some training data, we do have some labels for the training data, and we would like to train a model, based on these labels, on this input data, that can kind of make predictions in unseen in a generalized setting. Okay, so typically what you see now in the following, we often see these graphs, right? We have an x-axis and we have a y-axis. On the x-axis, this is our input feature. Right? In this case, we have a one-dimensional input feature. It just goes from, 0 to some floating point number, right? This is the input to our model. And we have y. Y tells us what is the prediction for the given input, right? Y, whenever we're talking about y, this is our expected prediction that the model should make. And specifically, y is typically the ground truth. We will later see what the predictions are. Predictions are going to be y hat. So I'm going to have a little hat over it. But if you say y here, y is the prediction of our sample, right? So in this case, the goal of linear regression is we would like to find a model that explains the target y given the inputs x. And in fact, what I can do is I can write down that I can plot the training samples here, right? I just put them all in this curve. So every orange dot here is a single training sample, meaning that for one x, this is x, I know the respective y, I know my target ground truth. And what I would like to do in linear regression, I would like to find this line here, right? I would like to find, based on this training set, I would like to fit a line. Again, it's a linear regression, that's why this is a linear model, to these training sets. Now, if you're looking again at these orange dots are the data points. These data points are, every data point has an x, that's the input, and a target ground truth, which is a y. In this case, we have n data points that go from x1 to n and y1 to n, right? So one pair of x and y is one data point, and we have the set of data points that go from 1 to n. What we would like to do now is we have a learner, and this learner is composed of some model parameters theta. Typically, we're going to use theta here that denotes the model parameters. Later on, we will see these are parts of a bigger model, right? Like a neural network. We're going to denote these ones, and again, this one is our ground truth data. Okay, so here we have, I mentioned it, right? We have input is x. What is an input? Could be an image, right? This x could be higher dimensional. In an image, it's very high dimensional. It's the number of pixels. Number of pixels that we feed here in its input determines the dimensionality of one single x. We also have the labels. In this case, these y's are either 0 or 1. 0 is a cat, 1 is a dog, right? The y's are the labels. Yeah, and this is what we want to do at training. At training, we want to take all these data points here. We have our learning method, and our learning method spits us out eventually some model parameters, right? And now, assuming we have trained, we can do testing. Testing means, I'm also going to call it often validating, because again, don't use the test set. This is testing, but it's not the test set. If you're doing that, we're taking here the xn+1th input sample. Again, this is not part of this training corpus here. This is a newly unseen sample, xn+1. I'm taking the model parameters theta. I'm feeding these ones into our model. And we're going to get an estimation, a prediction for that newly seen data. Right? So xn+1 is input, and yn+1 hat is the output. And yeah, in this case, we simply using the model parameters here to predict y hat, n+1. I already mentioned one thing. This theta here right now is defining a plane, but later on this will be our neural network. But same concept, just we have a more complicated model with more parameters. But again, we'll go into that later. Okay, this is the basic concept. We do training. Once we are done with training, examining the data points x1, y1 to xn to yn, we have the model parameters, we use the model parameters, and then we can apply this trained model onto newly seen data, in this case xn+1, and we can make a prediction for this newly seen data. Okay, if we're going into our model, we would like to have a look at what a linear model means actually. And by definition, a linear model is simply a dot product. It's going ahead and saying we have here the thetas, these are our weights, our model parameters, and we have our x's, this is the input. Now, this is our input data. We're gonna call these features. And we have, in this case, we have two indices. We have I and we have j. And this is very important. For the theta, we also have j, and we have, for this y, we have I. So the I is gonna be the ith sample. yi is the ith sample we are predicting, right? So for x is actually also a vector. We have xi is a vector that is composed of this d-dimensional feature, right? So we have, in total, we have I times j inputs from the entirety of the training corpus. One training sample is going to have d-dimensional inputs. And this d is parameterized by j here, right? This tells us which feature we are considering. And for every feature, we're going to have one weight. So depending on the dimensionality of the input, we have that many weights and that many model parameters, right? Okay, so this is our input data, the features x. We have here our weights, the model parameters. We have d of them, they're parameterized by j. So there's an input dimension of d-dimensional input, and we're predicting the current feature yi hat, the current prediction yi hat. And again, whenever there's a hat, that means it's a prediction. Whenever there's no hat, that would mean it's going to be a part of the training. It's a ground truth. Okay, yeah, all I'm going to do now is I'm going to go ahead and going to multiply that thing out here. I'm going to make another small change in this linear model. I'm going to introduce a theta 0, but otherwise I'm just going to take the sum that we just had here, right? I'm going to add a theta 0 that is independent of the input. And then I'm just going to multiply out this dot product to have, theta 0 plus xi1 theta 1 plus xi2 theta 2 plus and so on until I end up with xid theta d. Yeah, the one thing I didn't explain really well is like, what is the theta 0? This theta 0 is a bias, and the bias is independent of the features of the input. And since it's a linear model, and we're plotting our graph again here with here's our x, that is our input, right? Y are our predictions. Here the orange things are our samples. This theta is going to be at x0, where the decision boundary or the regression line intersects with the y-axis, right? This is our bias. Now I would like to go to a concrete sample. How this works in practice, right? Essentially what we're doing, we're just having this dot product now. theta is the parameters we're trying to get from the training process, and then we can make predictions y I hat. So let's take a simple sample like the temperature in a building. I can tell you right now it's pretty warm at the moment, so there must be some pretty strong indicators that the temperature is high. If we are looking at the temperature, there could be a couple of combinations that determine the temperature in a building. Could be an outside temperature, this is our first feature, right? There's the level of humidity, that's our second feature. There's the number of people in the room, that's our third feature. And there's the fourth feature, which is like the sun exposure, like basically is my room being exposed by the sun. And all of these input parameters are being fed into our model. And based on this model, we are getting the thetas. These are our model parameters that weight these input features. In this case, it's a linear model, meaning that they're being weighted linearly. So everything is, there's a linear dependency between every input feature and every prediction. And then we're just taking one by one, right? And we're making a prediction. There's a little bit of an inaccuracy on the slide here. In this case, we're talking about x1 and theta1. This one here means it belongs to it's the first feature. It's not the first sample. Like in practice, we would have xi1, which would correspond to the first one, right? Okay. Let's write this down in a matrix. Let's make this a little bit, let's formalize this a little bit more. So let's say we have n samples we want to predict. So we have y hat 1, y hat 2 to y hat n. We have a bias. And then we simply write our samples from the inputs, these x's, we just write as row vectors into a matrix, right? So this thing here is the very first sample that we want to make a prediction for. This is x1. And x1 is composed of d-dimensional features, meaning that it's going from x11 to x1d. For this input here, right, we would like to predict y1 hat based on our weights. And the way we do this is we're essentially doing a matrix vector multiplication. So we're multiplying this row here, with that column here, right? And we're getting this we're getting this y hat 1. And we're adding the theta here to formulate it a little bit more nicely. We just put this guy here into the matrix. So now we have here the ones, right? And then we can do literally this matrix vector multiplication. This is the math behind it. In practice, we write it in matrix form. We'll more get to this later. It's just easier to do in this way for a linear matrix file. Okay. Again, here we have our input features. This is determined. One sample here has d-dimensional features. These are our model parameters. Again, theta 0 is our bias. So we have d weights and one bias. The reason why I'm kind of explicitly writing it down this way is because in the neural networks, the bias has also kind of a special meaning that we will get to. Okay, but let's take a practical example. Let's say we have a bunch of our input features, outside temperature, humidity, number of people, and sun exposure. These are our x's that we're feeding in. We have here our biases. Bias we just set to 1, that makes it simple. Here are our model parameters. And what we do in order to get the temperature predictions of the building is we're taking all these parameters and multiplying with the model parameters here, right? Okay, so let's have a look at the number of people. So here in this sample, we have 2 number of people in the room. Here we have 0 number of people in the room. And our model tells us there's a 1 here. If I have 2 people in the room, I'm multiplying this by 1, meaning for every person I have in the room, my temperature will rise by 1 degree. That's literally what this model is telling us right now, right? It's very straightforward. We can look at the sun exposure. If we're getting basically more sun exposure, we're multiplying the sun exposure parameter with 0.14, which means, like sun exposure had a smaller impact on the model because this is a 1, this is a 0.14. But it is still a linear dependency. Twice as much sun exposure means twice as much contribution from that part of the input feature, right? We can also look at other parameters here. We can look at the humidity. Humidity has a 0 here. If there's a 0, that means this feature will not be considered. In other words, the humidity does not influence our model for predicting the temperature, right? So that's something that we should consider here. Okay, yeah, that's basically it, right? And at the end of the day, we're gonna make some predictions, and we either predict it's sunny or it's snowy, right? Depending on whatever we've learned in the model. We will, for a certain set of input features here, be able to make predictions. Well, and this is very nice, and I'll later talk a little bit about why this is cool. Even with a single model, you can basically abstract very complex phenomena into a very, very simple linear regression. The big thing what we have talked about right now is so far we've taken a model, we can evaluate the model, and we can make predictions. The thing what we have not talked about is how do we actually get this model parameters, right? How do we get the model itself? And this is the learning process, and this is what I would like to talk a little bit about right now. So in the learning process, what we're doing is we're taking data points as input, right? I mentioned this is our X. Whenever this is like bolded, this means like it's bolded and capitalized, that means it's a matrix, right? So the matrix has the number of columns is equal to the number of input features, and the number of rows is equal to the number of samples, the number of data points here, right? We're taking these data points. What we can do is we can run them with the model parameters that we just have right now. We just take an initial set of model parameters and we can make predictions of that, right? So we X input, model parameters theta, linear model, so just multiply them, right? We're getting some estimation Y hat. And then what we can do is we can check how bad or how good is our Y hat compared to our Y. And this, like how good, this goodness here is our loss function. And this loss function, assuming, well, Y hat is equal to Y, then we're pretty good, then we have a 0 loss. But assuming this is not equal, and that's most of the case in machine learning models, if this is actually equal, then we typically did something wrong. We'll later see that. But we will basically take the information from this loss function and update our model parameters accordingly, right? And this is part of an optimization. This optimization procedure will take the loss functions of all the training samples into account and will update the model parameters theta in order to minimize the loss. Okay, so if we're formalizing this very quickly, we have a loss function. The loss function, it measures the goodness of the estimation that we're having with the current model, like how good is my model right now. And the loss function can then be taken into account by the optimization in order to make the predictions better, in order to optimize for better model parameters theta, right? So the optimization then changes the model in order to improve the estimates, in order to minimize the loss. Okay, let's have a look at our linear regression because it's a simple example. What's the loss function here? Well, again, we have a bunch of training samples. These are our training samples here right now. Every dot here is a training sample. We do have the input X, we do have the predictions Y, that's denoted by every data point, and we have this regression line here. This is the prediction of the temperature right now in the building, for instance. And now what we can do is we can compute a loss function, and the loss function is simply computed by assuming we have this line that is our hyperplane that is defined, or that is currently defined by our current set of model parameters theta. We can take the distance from every point with respect to the line and can compute a loss based on that. We simply just sum up all the distances, the length of these green arrows here, that gives us the loss function, right? So assuming we have like one sample that is a bit more in the outlier, that would tell us, oh, we have a pretty big loss here that we want to minimize. And the way we would minimize it, we would simply move this line up, right? This is kind of what this optimization of the loss function is doing. In this case, it might not be a smart move what we've done here, but it's just, for illustration purposes. But the goal of the optimization is to minimize the loss function, minimize the length of these distances here, right? Okay, then we would recompute the loss and so on. And mathematically what we're doing, right, we're taking every prediction that we're making, we're subtracting it from the ground truth labels. So this is our target. We subtract these two, we compute an L2 norm here. So we take the sum of the squares we're normalizing by the number of samples. So we make the reason why we normalize it is because we want to make it independent of the number of samples. And J then is this function that we would like to minimize, right? And this one is dependent on theta. You will hear different names for it, especially in the deep learning literature. Like traditionally in optimization, this is simply an energy function, optimization, objective function, cost function, whatever, right? These are the three common terms, but we want to minimize it, right? This is the main thing. So we want to find thetas that minimize that function. Okay. Yeah, this is a linear least squares problem, of course, right? Everybody who is taking a calculus class knows that. This is not very complicated, but this is essentially the approach here is we want to fit this linear model to our data. So we want to find the minimum of this function, and we want to find the optimal theta that, in a least square sense, optimally explains the data, right? Well, the good thing is it's a linear problem. So since it's a linear problem, it's convex. It's a linearly squares function. This is why it's a convex problem. That's by definition the case. And that's very good, meaning that there exists a closed form solution, and the solution is also unique. Yeah, I wanted to highlight this one here again. We have here, in this case, we have n training samples. These are the predictions yi hat. Because it is a linear model, remember how we did compute yi hat? Meaning we simply take yi times theta, right? There's a little bit of a trick here mathematically. This yi here includes the bias, basically. There's a 1, the very first feature input here is 1, otherwise we don't have the bias. This is just, for simplicity, I didn't write the bias explicitly out here. Okay, but yeah, the predictions yi hat is by this dot product of the input features times the thetas, minus the ground truth. We have the sum of the squares here, and the estimation comes from the linear model, right? I mentioned it before, we often write it down in matrix notation. It's just so much easier. It's very straightforward, right? This is a squared function, so we have x times theta minus y transposed times x times theta minus y. And we optimize for that. Yeah, we have n training samples. Each input vector has d. So the dimensionality here is basically d times n. If you consider the bias not part of d, then it's d plus 1 times n, just, for simplicity here. I didn't want to write it down, but just be clear about it. The y here is the labels. This is what we have in the ground truth information. So in the exercise session, we will talk a little bit more about the matrix notation, but I hope you get, the broad concepts. Okay, now in order to find that, I already mentioned it, we have a convex function, right? So we have some sort of starting point somewhere here maybe, and what we would like to do is we want to find an optimum which is at the bottom of this quadratic function. Why is it a quadratic function? Well, it's a linearly squares problem, and because we took the L2 distances here. Well, if you've done a lot of optimization, you always know when you have a quadratic function, it's super easy to optimize. You're getting basically, well, if it's a linear model, you're getting a convex optimization problem. Okay, if you're having a problem and you want to find the minimum in this case, we follow the standard procedure. We're using a gradient-based optimization, meaning that we're computing the gradient of the cost function j, and we're setting it to 0. Well, if the gradient here is 0, well, it's a 2D problem here, so if the derivative here is 0, that means there's no slope, right? That means we have reached an extremum. Well, and I mentioned it's a squared problem, so we have a closed form solution. There will be some details in the exercise again, but it's straightforward, right? We're just taking j, we're deriving it with respect to the theta. This is what we're interested in. Our derivatives then will be 2 times xt times x times theta minus 2xt times y. We're setting it to 0 because we want to find the minimum. And then we can just simply solve for theta. Well, the way you do this, you first bring the 2xty to the other side. That's this part here. And then we're computing the inverse of that one here, of xtx, computing the inverse and bringing it also on this side. And the 2 cancels out, right? We're just dividing by 2 here. One thing to say, if you're doing optimization, you practically don't compute the inverse, you rather solve the linear system. But that's also something I would like to defer here. I hope you have talked about this in calculus. But how to solve a linear system is something you might want to look up if you don't know it right now, because this will be relating later to a couple of optimization methods we want to do in the context of neural networks. Okay, good thing is we found an analytical solution for a convex problem. If you're going back to our original sample, right, these x's here is our feature vectors. In this case, it's a feature matrix, right? We're going to have the outside temperature, number of people, stuff like that. This y here is our ground truth, and we're optimizing for that, right? Okay. Question now, is this the best estimate? This least squares estimate that we've been doing. So mathematically speaking, if we're having a linear assumption, of course we're finding the best solution. But one thing we would like to talk about right now is, how does this estimate actually relate to the practical observations we're making? And I would like to talk a little bit more in a probabilistic sense right now. Let's say we have an infinite number of samples. How do we kind of consider dealing with these distributions of samples that on one side we model and on the other side we observe? And this leads us to the maximum likelihood problems, or maximum likelihood estimates. I would like to talk a little bit about that one, because the maximum likelihood estimate will lead us essentially to various loss functions we're going to use later on. So we've talked about the linear regression, right? Now what I've mentioned, we would like to talk a little bit about the distributions that we're observing and the distributions that we are modeling. So we have two data distributions, P data and P model. So P data is nothing else but our training samples, right? So in this case, this is nothing else but our real world observations where we have ground truth. So we have here X as input, and what is the prediction conditioned on X, right? This is our true distribution that happens in the real world that we're observing. Let's say we can observe every possible event ever made, right? Then this is a continuous distribution. Our model, on the other hand, it makes also predictions, but the predictions are dependent on the X and on the thetas. Like, based on our model parameters theta, we can control our distributions based on theta. So this is our parametric family of distributions, and it's parametrized by theta. Now, the idea of the maximum likelihood is to connect these two things, right? So we want to make sure that our model kind of correlates to what our data is doing. So more specifically, the maximum likelihood estimate is a method of estimating the parameters of a statistical model given the observations. So in other words, we want to find our model, right? Given the observations from the real world, from our P data, right? To be even more specific, we want to do this by finding the parameter values that maximize the likelihood of maximizing the observations given the parameters. In other words, we want to predict what we observe, right? Or in other words, if you have a training and a test set, right? If you're training it on a train set, we would like to make sure that we're explaining what's on the test set later. At the same time, we already want to train on it in the sense that the test explanations will be in this distribution that we're predicting. Okay, there's one key idea about a maximum likelihood estimate, and that is the MLE assumes that the training samples are independent and generating by the same distribution. And well, what does that mean? What's very important here is this independency assumption, right? So what you can do is you can have a model, right? And the model again makes predictions based on some input X and some model parameters theta. And we have a lot of i's here. These i's are the number of samples that we're drawing from, right? And the assumption is, in order to reflect the real world distribution, right, we would like to make sure that this is basically the combination of all the predictions, and because these are independent, we simply multiply them together. That's why I have this product of all of them. And this is from our model, right? And the model, again, is parameterized by theta. And that this equality here holds because of the independency assumption here, right? And the idea of the maximum likelihood estimate is now, well, we simply want to find the optimal theta that maximizes this estimate this is this maximum likelihood estimate, theta ml, that our model corresponds to the observations, right? So it wants to maximize that likelihood. Typically what people do is, when they're thinking about maximum likelihood, they don't like this product here. And this product means that each of these things have to be considered in this kind of in sequence, right? You have to go through this whole product. The nice thing is here, we can relatively easily rewrite this function by taking the logarithm of this one here. The nice idea of the logarithm is, it's actually a monotonic function. So we can take the logarithm here, we don't change the argmax. So if theta here maximizes this one, theta will also maximize that one. And the nice thing about the logarithm is here, we can basically rewrite this product into a sum. So in this case, we have argmax theta of the sum of the log probabilities of our model. And we rewrote this part. Again, logarithmic property, like log a times b is equal to log a plus b. And we just did this for this entirety of the product here. And we rewrote it as a sum. And that's a pretty good thing, as we will see in a second, because now we have a significantly easier formulation here. And it does the same thing, meaning that the solution of this formula is the same as before, but we have a sum here. We're looking at our distribution of our p model here. And the question is, what kind of shape does that part here have? And that's something we would like to have a little bit a closer look in the context of the linear regression that we talked before. So we want to figure out what is the probability distribution here. So yeah, we're writing down p. And a lot of the times when people do this, they're going to tell you, oh, we make a Gaussian assumption. So in other words, we're assuming that this y here, right, it can be expressed as drawing from samples from a Gaussian distribution. So we have a normal Gaussian distribution. This one has a mean and it has a variance, standard deviation squared here, right? What you can do is you can just, move this part from our linear regression out. So we have xi theta plus the normal distribution centered around 0 with our standard deviation, right? Well, now what we're going to do is we're just going to rewrite n, right? N is our normal distribution, and it's 1 over the square root of 2 pi sigma squared, right? Times e to the power of -1 over 2 sigma squared times yi minus mu squared. And the idea now is, what we can do, we can figure out how to rewrite this part. And we can simply say, well, we're just using our Gaussian to replace it. The way we do this, we know here's our mu of our Gaussian. And what we're assuming here, we have here our mean that is given from our linear regression, right? So we simply put this one into our mu. This is the mean right now. And then we can rewrite this probability distribution here with this Gaussian assumption. And we simply have our linear model in here, right? What we've done here, like this part is the same as this one, right? This is just rewritten. But all we've been doing is we have made this Gaussian assumption. And now we can go back to our maximum likelihood estimate. So now what we're doing is, well, we're saying, hey, we want to find the optimal parameters theta under this Gaussian assumption. What we can do now is we can take the logarithm of our model, meaning that this p model we've just written here as this one. So we feed in this one in here. Okay, so let's do that. And the nice thing is, and this is another advantage that we took the logarithm here, the logarithm will basically cancel out this e function, which is nice, right? So here we have the sum of the log probabilities. Log and e cancel out. So all that remains left here is basically yi minus xi theta squared. And we have some constant factor. By constant, I mean this one is not dependent on the x's. This is just dependent on the sigmas, basically. We can write it as matrix notation. Again, more matrix notation in the exercise session. So it's 1 over 2 sigma squared, right? Y minus x theta transposed y minus x theta. And yeah, if you're writing this one down, basically like we can write now this model into this very nice matrix form. Now, the good thing is we have this constant factor here, and this factor here is not dependent on the x's and the thetas. in this case, what we want to do is we want to find the thetas. So we do the same trick as what we've done before. We're saying, oh, if we're taking j of theta with respect to the partial of theta, we're computing the gradient here, we're obtaining this very simple function. Why do we get that? Well, this one here cancels out, right? And all that stays is the rest here. We will go over this again in the exercise session, but the nice thing here is this is nothing else what we had before when we did the least squares estimate, right? So if we're making the maximum likelihood assumption, well, we have this maximum likelihood under these assumptions, right? We have this independence of the samples, and we have this Gaussian estimate. Then the maximum likelihood estimate corresponds to the least squares estimate, again, given the assumptions. But this is a very simple derivation, basically, that correlates these two things. In other words, the linear regression is actually doing something very reasonable because it corresponds to maximizing the probabilities, assuming these assumptions with a maximum likelihood estimate, right? Yeah, we've introduced a bunch of concepts now of the loss functions. And we introduced a little bit of ideas how we could potentially optimize them and obtain the best model for the regression. We've talked a lot about the regression. We had this example of the temperature, but I would love to go back to the image classification case. And I would also like to take the opportunity here to explain the differences between regression and classification, because we've often done that now, that I just mentioned it, but I didn't really go into a lot of detail here. So if you're talking about regression versus classification, the regression is very clear, right? We're predicting a continuous output value, like the temperature in a room, like what we had before. And the classification, on the other hand, is we want to assign a discrete label to a given sample, like training test sample. We thought about binary classification, like 0, 1, dog versus cat. We can also talk about multi-class classification, when we have n classes. However, to keep it a little bit simple, I would like to talk about this 0 and 1. And now the idea is, we've talked about this linear regression, which is this formulation that we have a linear model that can predict any arbitrary value, any arbitrary continuous value. The question is, how can we map this one here into a binary classification? And the idea here is that the output is between 0 and 1. That is, we want to interpret the outputs of a regression as a probability distribution that we can then use to, have a threshold of, let's say, oh, it's greater than 0.5, then it's this class. If it's smaller than 0.5, then it's this class. So it's the decision boundary there. And this is a thing we can do with logistic regression, right? In this case, we want to develop our amazing cat classifier. We want to take the input image here. We want to learn this classifier and want to tell us that this is a cat. And all we're doing right now is we're starting with our linear classifier. So we're taking x0, x1, x2. We're taking this dot product with three weight vectors, with three weight scalars. We're summing them up together. Again, simple dot product. And now what we want to do is we want to have the squashing function that squashes everything between a 0, 1 interval. Like we want to make sure out of this one, we're always getting a function that maps between 0 and 1. And a lot of the times people use a sigmoid function for that. A sigmoid function is defined by 1 over 1 plus e to the power of minus x. And this function looks like that, right? So it is basically, it takes a maximum value of 1 and it takes a minimum value of 0. So it is basically interpreting it. You can interpret the output as a probability because it's between 0 and 1. It grows kind of exponentially at the beginning and then it plateaus at the end, and it's symmetric here around 0, right? And it crosses the y-axis at 0.5. And yeah, so all we're doing right now is we're taking the output of a linear regression and feeding it into a sigmoid function, and this is what logistic regression is. So we're mapping it between 0 and 1. And we interpret this as a probability. So now our probability is our label could be either 0 and 1. In this case, our label yi is 1. Model theta, input x, right? And this is our distribution we want to model here. Okay. Small spoiler alert. This is a one-layer neural network. We will later build up on this, and this is the reason why I've been talking so much about our linear model here, because this is our linear part, and then we have a non-linear part. and the combination of these two will be a neural network layer. But more to this in the next lecture. You have to unfortunately wait another lecture, which means another YouTube video, where we go into that. But I would like to go into a little bit more detail into this function here right now. Okay, so logistic regression is a probability of a binary output, right? To be more precise, we're making predictions y hat here. What is the probability that we're gonna get this label 1 for input x and the parameters theta? We're doing the same thing as before, right? We're simply multiplying all the probability over all the yi's together, right? Of all of them at the same time. We're considering the whole distribution by taking all the data at the same time. And we assuming this logistic regression model. And the predictions that we are making, to be precise, they're going to be y hat I is equal to the sigmoid function of xi times theta, right? Linear part in the middle here, we're taking standard linear model. Again, simplified it a bit, there's a bias in there, didn't explicitly write it, just for the case of you knowing this is actually going to be in there. In a neural network sense, I will be a bit more precise, but I wanted to keep it simple. We're feeding in a sigmoid function and we're getting our probability output. Now we can also rewrite this function a little bit, and this is what people typically do. Since this is a binary output, we could think of this as a Bernoulli trial. All we're doing is we're taking now the model of coins, meaning that here we have the probability that we're predicting z based on phi. We're having this Bernoulli trial here, and all we're going to do is we're taking this formula here, and we're putting in this formula our predictions here that we're making with our sigmoid function and the linear model in between. Okay, so we're going to write this quickly. So the predictions here of our sigmoid will be our phi. So we're writing it this way. Again, we have our product of our samples, right? So this is our model of the coins. Well, write this down maybe, right? We have this one here. We're just replacing the phi's here, respectively, and the z's with the predictions. We're ending up here with the predictions to the power of the labels, and so on. So we're having here the predictions of the sigmoid. That's a continuous output because that's our probabilities we're getting. And these yi's here, these are discrete labels. They're either going to be 0 or they're going to be 1. Nice thing. What we can do is, same trick what we did with the maximum likelihood estimate. We can rewrite this a little bit. So I quickly want to start from here. This is going to be our loss function. So now we have, we have here our y hat, right? We have the product of these terms. And now we're taking this nice idea of the maximum likely estimate. So we're saying, well, we're maximizing the likelihood here. We're finding the thetas that maximizes the likelihood by taking the log of the probability. Again, this log is a really cool function because it will eventually make this one here cancel out. So we're taking the log here, again, starting from this one here. Now we're taking the logarithm of all of this kind of stuff. And well, since we have here this, we're rewriting the product here again with the sum. And the nice thing is here, the logarithm and the exponential functions cancel out, right? Well, it doesn't cancel out, but we can rewrite it. We can just bring this yi here to the front and this 1 minus yi here to the front. And this function drastically changes. The reason why we can do that is very simple. Again, the log function is a monotonic function. So finding the optimum before the log is the same as finding the optimum afterwards. But this allows us to rewrite this and simplify this by quite a bit. Okay, now this gives us the loss function. Our loss function here is measuring the distance between the predictions we're making, and it measures the distance between the predictions we're making yi hat and between our ground truth labels, right? And this is the term we're ending up with for a given sample yi. Of course, if we're going back, we still have the sum over all the yi's, right? We have n samples we want to evaluate on. These are all of our training samples then, right? Okay, good. So let's have a look at the case if we have the positive samples. So we have yi equal to 1. The nice thing is, if here is a 1, this term here cancels out, right? In this case, we only have the loss where yi hat is being compared to the positive label. It's just the logarithm of yi hat. And in this case, well, we simply have this maximum likelihood estimate again, right? So we're trying to maximize the likelihood of this probability. So we have the log probability here. We want to make log y hat large. Since the logarithm is a monotonically increasing function, we also want to be y I hat large, right? And 1 is the largest value that this model can actually take, which is very nice. We also can take the other case, right? In this case, in the 0 label case, this part here cancels out, and all that remains left here is the logarithm of 1 minus y hat I. In this case, we want log of 1 minus y hat I to be large, so we want yi to be small, and 0 is the smallest case that the model can take. Oh, yeah, why is that the case? Well, we have a sigmoid function, right? So this is based on a sigmoid function. This is the output of a sigmoid function. 0 is the smallest one, and 1 is the largest case here, right? This was the other one if you're going back, right? Okay, good. So this is a good loss term to memorize, and we have derived it basically by taking the maximum likelihood estimate. And we've taken the sigmoid function that nicely maps the output of a linear model between the 0-1 range that we can interpret as a set of probabilities. Because it is the probability, we can use the maximum likelihood estimate, and then we can rewrite the function like that. And this function here is called the binary cross entropy. It's often abbreviated as BCE. Later on, if you use deep learning frameworks, you will see BCE quite a bit. And yeah, this is a very important function we're going to use for quite a bit. And in practice, what we've done is already a one-layer neural network that we're going to build up on in the next lecture. Okay, yeah, I refer to this as a binary cross entropy. There's also the multiclass loss. This is called a softmax later. This is very related to that. We will talk about this into a bit more detail. Now we have this loss function, and what we want to do is we have, based on this loss function, we just sum over all the samples. That gives us the cost function. The cost function is the sum of the loss functions over all samples. We normalize it typically with respect to the number of samples, so it's independent of the number of samples. And we want to minimize that function, right? And we can then write it like that. Again, to memorize, this yi hat is sigmoid of this linear part, right? The interesting thing now is, of this logistic regression, when we want to optimize that, there's no closed form solution anymore. So we have to use an iterative method to find the optimal solution. This is being done with typically with gradient-based optimizers. There's other optimization methods. We will talk about these ones. But for the most part, we will use a version of gradient descent. By the way, for all the German speakers, it's gradient descent and not gradient descent, which a lot of people tend to say. Okay, but we will definitely talk about this a little bit, actually for quite a while, and there will be also a couple of variations we will talk about. Okay, so this is basically the main technical content I wanted to go through today. What we've seen now is we have seen what is a classifier, we've seen basic machine learning concepts, we know what a linear model is, we also can map a linear model to this probability with the sigmoids. That's what the logistic regression is. But I still wanted to take a few minutes here and explain why I think like this whole machine learning is actually really cool. That's why I'm so excited about it. The nice thing is we can learn from experience, and that's what humans do all the time. In fact, I would say, the intelligence is kind of this idea of, based on the current information, how much can you infer the future, right? How much can you abstract from that? Like, how much information do you need and make reasonable predictions what will happen? And this is I think this is a cool concept. You can apply it to so many new things. And the good thing is often, if you don't know what to do, you can always apply a machine learning method for most cases. Not always trying it. I'm not saying like everything has to be solved with a neural network, but this applies to so many cases. So the nice thing, even what we've learned right now, is that the linear models, they are often pretty good for complex phenomena. Like these, like weather predictions or like temperature predictions, they're super complicated. To simulate them, it's like crazy expensive. But give me like the time of the year, give me a day, let's say I'm gonna be in the middle of December, it's in the middle of the night, based on a linear combination, of these features as input, I can probably make a reasonably good prediction of the temperature. Right? It's not perfect, of course, it's the linear model. I mean, what do you expect? But with very simple things, you can make very, very good predictions. And this is a nice thing that is amazing. And humans do this all the time. Humans just do it just much better than what we can do with machines. But the exciting thing is we're getting much, much better with machines now, and we can do more and more cool things. I wanted to mention a quick other example of logistic regression. Since we're talking about fitting curves and stuff like this, the main reason why we're all here, quote unquote, on YouTube, is that we have this interesting coronavirus situation. And if you looked at these curves, they all look like sigmoid functions, right? There's not just a pure exponential function, and there's a very simple reason behind it. At the beginning, the exponential curve grows, but then it plateaus at the end. And the reason why it plateaus is because you can't infect more people than you have in a country. It's very simple. I took one of the curves here from South Korea, right? You see it grows exponentially at the beginning, and then it plateaus at the end. Now, why is it interesting for machine learning? So the machine learning problem is here, give me a new country, maybe you're only at the beginning of this curve, based on a certain set of features of the country, tell me how your curve will develop, right? That's basically machine learning. So with the power of machine learning, we can think about where are we right now here in Germany. We're not quite so far ahead in our curve, and we can of course hope the very best for our curves. But we have this exponentials at the beginning, like how the curve grows. By the way, don't let you fool that this curve is very flat here. I can just rescale the axis here to make it less flat, just to clarify that part. Don't be fooled by like what people show you without looking at the axis labels. But what's very interesting about it, right? We're still relatively at the beginning here in Germany at these curves, and with machine learning, in principle, you can predict it. Of course, once you can fit the full curves, it's easy. But the question is, when you're very much at the beginning, you're relying on some prior experience, basically from other countries, for instance, how these curves will develop in the end of the day. And this is what machine learning models are actually pretty good at. And now the interesting thing is, of course you have to choose the model. We'll get to this in a second. But the big question is, what features do you want to use? And this is something that you still have to do by hand for most of these machine learning models. If you're talking about the corona curves, there's a lot of features. There's the features of population density, implementation of measures, reasonable government, right? Like, what's your government doing? Is your government trying to tell everybody, oh, we get herd immunity, everybody gets infected? I'm not naming any countries here. But if that happens, then your curves will look more like that, right? Of course, like these things you can abstract from. And the question of machine learning is basically, how can you take these features and put them into a machine learning model and then make these predictions? And that's one of the reasons why I think machine learning is cool. If you have enough training samples, we can abstract complex phenomena with like that simple math and get very, very cool predictions out of it and can infer the future that maybe other people wouldn't be able to do. That's maybe one of the reasons why so many people are interested in the deep learning courses. The model matters, of course, too. We have done very simple models right now, right? We have done linear and logistic models. There's many more models, of course, and we will develop very complicated models along with the neural networks. Coronavirus, well, the model matters, right? You can't have more infections than total population. If your model already makes these predictions, then your model might not be very good at. There's also other models, right, where logistic regression wouldn't be a good example. One of my favorite or least favorite examples is the housing market in Munich. This one seems very exponential, right? There's no limit in terms of how high can the rents go. Like Munich is growing exponentially, and there seems to be no limit. I don't know if there's a limit, but so far it doesn't seem to be. So maybe we need kind of a different model for that. Okay, I was, according to my timer here, I'm 5 minutes over. I would like to end the lecture for the time being. Again, I would like to remind everyone that they're the exercise sessions. I think they're very important. I would also like to remind everybody to be, active on YouTube. Not on YouTube, active on Moodle, like participate on the course. If you have any questions, contact your TAs and so on. In the next lectures, we're gonna talk about now basically we have learned, quote unquote, this one layer neural network. We will build up on that, and we will build up on the logistic regression, and then we will develop more complicated neural networks in the next lecture. Okay, we added a couple of references here. You can look these ones up. I hope you all stay safe and healthy. Stay at home and enjoy reading your favorite deep learning books and deep learning problems, and have some fun soon when we give you the first exercises and math sessions. All right, see you next week. Stay safe, stay healthy.